Okay, so first, mathematical proofs. So a mathematical proof is a sequence of logical arguments used to show the truth or the truth value of a mathematical statement. So if you say that something is true, then you must demonstrate it logically that is true for all the stated cases. And so we have cases where it looks like things are true, and you may have a lot of data saying it's true, but just because you have a lot of cases where it's true, mathematically, that doesn't mean it's true. So mathematically, if you have a statement, it must always be true. Whatever your statement is, if you're saying it's true, then it must always be true. It's not like in other places, in psychology, sociology, where, well, sometimes true, or even in physics, well, it's mostly true. It has to be true in every single case. So, Mern's conjecture was some conjecture, and it was conjectured to be a true statement in 1885. And people started working on it, and they actually verified that it was true for the first 100 million cases. So they looked at 100 million numbers, and they all worked. But in 1985, it was shown that this conjecture was false. So even though you do it, and they actually worked a lot on it. I mean, to actually verify it for 100 million cases, people thought, well, it's probably a true statement, but it turned out to be not a true statement. So just because, you do it and it seems to be true, doesn't mean it is true unless you actually do a mathematical proof of it. So we will give you one way of proving something involving, if you are trying to do something that involves countable number of steps. And so if a given statement P sub n is associated with every natural number n, so that means that they're just a countable number of statements, then the statement P sub n is true for every natural number n, provided that the following conditions hold. P sub 1 is true, so the very first statement is true. Next, if we assume that P sub k is true, so P sub k being true implies that P sub k plus 1 is also true for any natural number k. So let's think of it as follows. As a game of dominoes. So, well, not the game of dominoes, but suppose that you're given a set of dominoes and you're by yourself, so you can't really play dominoes by yourself. So rather than actually playing dominoes, what you do is you line up the dominoes next to each other. So you have some domino, and then you put another domino next to it, and another domino, etc., etc. So you have a whole bunch of dominoes next to each other. And if you knock over the first domino, and knocking over any domino causes the next domino to fall, then that means that every domino will fall, because if the first one falls, that causes the second one to fall, which causes the third one to fall, the fourth one to fall, all of them to fall. And that is the principle of mathematical induction. It is a game where if the first statement is true, and if any statement causes the next statement to be true, then the first statement causes the second statement to be true, the third statement to be true, the fourth statement to be true, every statement to be true. And that is the principle of mathematical induction. So, what are the steps that we will follow for mathematical induction proof? First, I will state the initial case. Then I will show that the initial case is true, meaning P1. So I'll first tell you what P1 is, then I will show that P1 is true. Next, I will state the induction case. PK is assumed to be true. Oh, I will then show that the induction case is true, that if PK is assumed to be true, then that will imply that P sub K plus 1 is true. Then lastly, I will state the conclusion that mathematical induction shows that the statement is true or false, and one domino causes the next domino to fall. For any pair of dominoes that are next to each other, then every domino falls. So let me restate mathematical induction. P1 being true, and for every k, every natural number k, pk implies being true, implies that pk plus 1 is true. Then pn is true for every natural number n. So let me give an idea of what it means to be inductive, to have this sort of induction property. So to do that, let me construct some number systems. So first, let me construct the whole numbers. So construction number sets. So first off, the whole numbers. So the whole numbers is just a set 0, 1, 2, 3, etc. So I will assume these whole numbers, okay? So that's the idea. And so let's state the piano axioms, named after the piano. I think Giovanni Piano. First, the set of whole numbers is not empty. There is at least one number in it, and I'll call it 0. So exists some number, there exists some element, 0, in the whole numbers. So there is some whole number 0. Next, there exists some injective function S from the whole numbers to the whole numbers. This function will be called the successor function, meaning that every whole number has a next number. So 7 is followed by 8. 15 is followed by 16. So there exists this successor function. Next, there does not exist a whole number n such that the successor of n is 0. And so 0 is not the successor of any whole number, meaning that 0 is the smallest whole number. So if you look at 0, well, the successor of 0 is 1, but there is no number whose successor is 0. It would have to be -1, but that's not a whole number. So there is no whole number, whose successor is 0. So if you have any number like 54, well, the successor of 54 is not 0, it's 55. And so there is no whole number whose successor is 0. Next, mathematical induction. So this is going to be the principle of mathematical induction. It's assumed. So let A be a subset of the whole numbers such that 0 is an A, and if n is in the set A, then the successor of n is in the set A. If these hold, then this implies that A is the whole set of whole numbers. And so this is the idea of a principle of induction. And so the whole numbers will only be assumed to have these four properties invoked on a set of quantities, numbers. So we wish to define an arithmetic operation on this set. So let me just state this. If n is a whole number that's not equal to 0, so it's a natural number, then there exists a unique whole number m such that the successor of m is n. And that can be shown to be true from this, from these four axioms. Next, for every set A, for every function from the set A to the set A, if A is a member of the set A, then there exists a unique function G from the whole numbers to the set A, such that G at 0 is A, and G composed with a successor function S is F composed with G. So let me just show this diagrammatically with the diagram. And so to show this as a diagram, we use the following one here, and then a little arrow and an A and a number above it, or quantity above it. So I have 1, I have an arrow, I have a set A, and I have another quantity. Then this will denote that A is a member, that little a is a member of the set A. So that little diagram means that. Next, X, a set X, a set Y, this little dashed arrow, and F will denote the following. It'll denote that there is a unique function between, so there exists a unique function F from X to Y. Oh, and I guess I should say that I should state that here, that F arrow AB, well, let's say it this way, that X arrow Y F, that this denotes a function, okay, there it is, denotes a function F from X to Y. So I should say that also. So the above theorem here can be written a little easier as follows. And so it says the following. Well, 1 arrow W 0. So this says that 0 is in the set of whole numbers, okay? Next, this is just 1 goes to 1. So this is the identity mapping of 1. Okay. So obviously, if you do nothing, you just map 1 to 1. Next, 1 arrow A to, and with a little a over it means A is a member of the set A. So if 0 is a member of the whole number, so 0 is a member of the whole numbers, A is a member of the set A. W, S arrow W means that there is a successor function S from the whole numbers to the whole numbers. We certainly know that. That's the so that's the so that's that axiom. Uh, there is a unique function G from the set of whole numbers to the set A. There's a function F going from A to A. There is a unique function G going from W to A. So this says, well, for every A, little a in X, given, and for every F, mapping from the set A to A, there exists a unique function from the whole numbers, the unique function G from the whole numbers to A, such that this diagram commutes, meaning that going in this direction is the same as going in this direction. That G composed with S is the same as F composed with G, which is the statement here. And seeing that these compose says the following, that G at Z is A. So A is G at 0. Oh, there it is, right there. And so this diagram is the statement here. Okay, so now let's see what this implies. Okay, so well, all I'm going to do is, and it doesn't really matter what I call this, but okay, so I have a 1, 1, W, W, S. None of these can be changed. So 1, 1, 0, W, S, W. So these are fixed. So I just rewrite that. Now, I'll call, so I need a set. Well, the only set I know of is W, is the set of whole numbers. So let's use the set of whole numbers. And so I'll use the set of whole numbers, and I need a function. Well, I really only know one function, the successor function. And I just called A M. It doesn't really matter. It doesn't matter if I called it A or M. I don't know why I called it M. I just called it M. Okay, so the above theorem says there exists some unique function G such that this diagram commutes. Okay, so we call this, I'll denote it by G superscript M, the subscript of plus the whole number plus. And so we have the following. By the above theorem, I replaced A here by W by the set of whole numbers. I replaced the function by the successor function. And for some reason I called A M, doesn't really matter. Then the above theorem said there existed a unique function, and I called it this weird notation, such that from the whole numbers to the whole numbers, such that, well, this commutes. And so, well, let's look at both of these, such that this commutes. So meaning that I have 0 is mapped, and then E is another mapping. And so I have that G at 0 is equal to, that's identity in M, is equal to M. So G at 0 is M. So G at 0 is M. I'm sort of getting rid of the subscripts right now when I'm saying it. So G at W is M. And, well, let's look at this guy. This says successor, then G, G, then successor. So it says that G of the successor of any point is equal to the successor of G. So it says that G composed with S, the successor function, is the same as the successor of G. We'll just denote this G superscript M plus as plus. It's adding M. So now easier notation. So this is G superscript M evaluated at N is just M plus N. And so this just says that M plus Z, and this says that, well, this notation says that M plus the number after N is the same as the number after M plus N. So 3 plus the number after 5 is the same as 3 plus 5, the successor of 3 plus 5. And so, multiplication. So you notice that in this case, this gives you addition. And there was really no other choice that I could have made for this diagram. So the only choice, the only function around was S, and the only set around was the set of whole numbers. If I use those only things around, I got something that will be what acts like our addition. Next, let's do the next one. So again, the only set around I have are the set of whole numbers. So I'll just use, for A, the set of whole numbers. Next, I'll use 0. I know that 0 is a member of the set of whole numbers, so I'll use 0. And, well, now use, well, let's see. If I did the successor function, well, I only had I had the successor function, but I've used that before. So let's use the created function that I just created. So I created this plus function. So let's use the plus function. If I use the plus function that we just found before, then there'll exist by the above theorem another function, the times function, the multiplication function. And so by the above theorem, with A being the set of whole numbers, F being this addition function we found from the previous construction, and letting A be 0. That was a convenient thing because we've already had some arbitrary number M here. So that will allow us to just not use any additional sort of things. Then there exists a unique function, G superscript M subscript dot sub w from the whole set of whole numbers to set of whole numbers such that, well, let's look at this. This says that, well, I'll see, since there's two G's, I'll say G multiplication, the multiplication G at 0 is equal to 0. So the G multiplication of 0 is 0. And let's look at this guy. This says that G multiplication composed with the successor function is the same as the addition function composed with the multiplication function. We will denote G superscript M subscript dot as multiplication, M times N. And so, now let's retranslate this into the usual notation. M times 0 is 0. Let's translate this. M times the successor of N is M plus M times N. Okay, so actually let me tell you what this means, the previous one. This says, well, M plus the successor of N is the same as the successor of M plus N. So if you add 1 to N and add it to M, that's the same as adding 1 to M plus N. That's what that guy said. Okay, next. What does this guy say? This says that M times N plus 1 is M plus M times N. And so it's just distributive property. Exponentiation. Okay, so again, the 1, 1, 0, whole numbers, successor function, whole numbers, those are fixed. I can't make any difference. I can't change those. The only thing that I can change is this guy, and these. Well, again, this. And so again, this is the only set around that I have is set of whole numbers. So I'll use the set of whole numbers. You can use a subset of the set of whole numbers, but I'll just use the set of whole numbers. I could use a subset, but I'll just use set of whole numbers. Next, I'll use 1 because that's, well, it turns out that that's a nice, convenient thing to use, and you'll see why. And I'll use, well, now I have the successor function, I have addition, I have multiplication. If I used addition, then I got multiplication. So let's use multiplication and see what happens. So let's use the multiplication function. And there exists a new function, which I'll denote by G superscript M subscript caret. Okay. And so this says, so by the above theorem, with A equaling the set of whole numbers, F being the previous thing that we defined, G superscript M subscript dot, and let A be 1, then, where 1, I should tell you, and maybe I should have written this, this is really the successor of 0. Because I know what 0 is. So that's really the successor of 0. Okay. Then, by the above theorem, there exists a unique function G superscript M subscript caret from the set of whole numbers, such that. Well, let's see what this says. This says here that G, the exponential, I'll call this the exponential G. The exponential G of 0 is the successor of 0. Well, I already said that 1 denotes the successor of 0, so I'll just leave it as 1. And we have that from here, G, the exponential G, the exponential function G of the successor is equal to the multiplication G of the exponential G. So let's denote G superscript M subscript caret of n as being m to the power n. And so m to the power 0 is 1. M to the power, the successor of n, is m times m to the power of n. Okay. And that's what this says here. So this says, well, let's see what this says. So this is exponentiation by m of the successor of n is multiplication by m of the exponentiation of m. So it just says that m to the power n plus 1 is m times m to the n. And that's what this says also. For convenience, we denote successor of 0 to be 1, successor of 1 to be 2, successor of 2 to be 3, etc. Okay. Now, I really should have just defined this from the set of natural numbers, but I didn't want to. So I should have done that, but I didn't want to introduce the set of natural numbers in that sort of fashion. So I didn't. Okay, so let's do the following. I want to show that 3 plus 1 is 4. So let's use the property that we gave here, these properties, only to show that that's true. So let's only use these two properties to show that this is true. And the notation, and this notation. Okay, so let's look at 3 plus 1. Well, 1 is the successor of 0. So by the above property, we have that 3 plus the successor of 0 is the successor of 3 plus 0. But we were given that 3 plus 0, well, that m plus 0 was always equal to m. So 3 plus 0 is just 3. And I'm given that the successor of 3 is 4. Okay. Let's show that 3 plus 2 is 5. Okay. Well, 3 plus 2 is, well, the successor of 2. The successor of 1 is 2. So this is the same as 3 plus the successor of 1. And by the above, we had that. This is the same as the successor of 3 plus 1. But 3 plus 1 we found was 4. The successor of 4 is 5. And so we've shown that 3 plus 2 is 5. Let's show that 3 plus 3 is 6. Well, 3 is the successor of 2. 3 plus the successor of 2 is the successor of 3 plus 2, but 3 plus 2 was shown to be 5, and the successor of 5 is 6. And so we've shown that 3 plus 3 is 6. Let's show that 3 times 1 is 3. 1 is the successor of 0. 3 times the successor of 0 is the same as 3 plus, by definition of multiplication, 3 times 0. But we know that m times 0 is always equal to 0. That was one of the given things that we discovered, that we automatically got, that m times 0 is 0. And so 3 times 0 is 0. Now 3 plus 0, well, again, by the magical construction of addition, we had that m plus 0 was always equal to m. So 3 plus 0, therefore 3 times 1 is 3. Let me show that 3 times 2 is equal to 6. Well, 2 is the successor of 1. Therefore, 3 times the successor of 1 is 3 plus 3 times 1. But I know that 3 times 1 is 3. And I've shown that 3 plus 3 is 6. So that's why we did that previous calculation, because I knew that I would need to know what 3 plus 3 was. And so we had previously shown that 3 plus 3 was 6. Next, I'm showing these so that I can actually do one calculation, really. 6 plus 1, I want to show that 6 plus 1 is 7. That should be pretty easy because the successor of 0 is 1. So 6 plus the successor of 0 is the successor of 6 plus 0 by the definition, by the way that we constructed addition. And so 6 plus 0, we found, again, that was just 6. Again, that was in the construction of addition. That we automatically had to have that any number m plus 0 was m. And we're giving the notation that the successor of 6 is 7. So therefore, 6 plus 1 is 7. Next, I want to show that 6 plus 2 is 8. That's why we did the 6 plus 1 first, because we want to show 6 plus 2 is 8. Well, 2 is the successor of 1. So 6 plus the successor of 1 is successor of 6 plus 1. But 6 plus 1 we just showed was 7. And the successor of 7 is 8. Yeah. So now we want to use this to show this. So we want this to show that 6 plus 3 is 9. Well, the successor of 2 is 3. Therefore, 6 plus 3 is the same as 6 plus the successor of 2, which is which we found by our construction had to be the successor of 6 plus 2. But we found that 6 plus 2 is 8. The successor of 8 is 9. We denoted by 9. So now let's do exponentiation. So the previous ones is because we want probably to show that 3 squared is 9. And so let's first do 3 to the power of 1. I want to show that that's equal to 3. Well, the successor of 0 is 1. Therefore, by our construction, we had that 3 to the power of the successor of 0 was just 3 times 3 to the power of 0. So we have that m to the successor of n was m times m to the power of n. But 3 to the power 0, we already showed was 1. No. So 3 to the power 0 is, by our construction of exponentiation, is 1. And 3 to the 1, 3 times 1 is equal to 3, because we already showed that. And so we showed that 3 times 1, there it is right there. We showed that 3 times 1 is 3. Now we want to show that 3 squared is 9. This is probably all I wanted, was 3 squared is 9. That's probably the ending statement. Yeah, that was the, basically all I wanted to do was show that 3 squared is 9. So all the previous stuff is to help me show this. So 3 squared is 9. Well, 2 is the successor of 1. And so by our construction of exponentiation, this is just 3 times 3 to the power 1. But we've already shown that 3 to the power 1 is 3 in the previous example. And so now I have 3 times 3. But 3 is the successor of 2. And so 3 times the successor of 2 is 3 plus 3 times 2. I've shown that 3 times 2 is 5. I'm sorry, 3 times 2 is 6. The successor of 5 is 6. 3 plus the successor of 5, by our construction of addition, is just the successor of 3 plus 5. Oh, I didn't show 3 plus 5. Oh, darn, I only got as far as 3 plus 3. Shoot. Okay, so I have to show that I should have done some more examples. And so 5 is the successor of 4. So 3 plus the successor of 4 is the successor of 3 plus 4. And I only did the 3 plus 3. So now I've got to do this one. 3 plus 4 by construction is the same as 3 plus, 4 is the successor of 3. And so this is 3 plus the successor of 3, which is the successor of 3 plus 3, which is 6. Successor of 6 is 7. Successor of 7 is 8. Successor of 8 is 9. So therefore, 3 squared is 9. So actually, I probably should have had like these last two things calculated from above, but I didn't. I guess I got tired of doing the same thing 20 times. Okay, so ordering. Let m be a whole number and n be a whole number. Then we say m is less than or equal to n if there exists some whole number k such that n is equal to m plus k. We say that m is less than n if m is less than or equal to n and m is not equal to n. We say that m is greater than equal to n if n is less than m. So that gives you the ordering on the whole numbers. Let's look at integers. And so to construct the integers, it'd be a little bit more difficult, but how we're going to have to construct fractions, the rational numbers. And so we want to construct a set of integers, meaning 0, 1, 2, 3, dot, 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 negative 1, 2, 3, dot, dot, dot. And so first I have to sort of tell you what a quotient set is. So let squiggle be the equivalence relation on A. For any A in the set A, let A over squiggle, the quotient. So A quotient squiggle, the equivalence relation, as equaling the set of all x's that are in the set A, such that x is equivalent to A. Sometimes we denote A quotient, this equivalence relation, as A, well, let's just say a little bracket, or just by A, such as 3 over 4 is the same as 6 over 8. So sometimes we don't, put them in little brackets or whatever. We just say, well, they're equal. Okay, so let the set A quotient, this equivalent relation, be the set of all A quotient equivalent relation where A is in the set A. This is called the quotient set of A. We'll define the integers as the Cartesian product of the whole numbers with the whole numbers, quotient out with the equivalence relation that we'll be defining for the set of integers. So two integers are said to be equivalent if, so A comma B, this is an ordered pair, it's in the Cartesian product, is equivalent to C, D, if A plus D is equal to B plus C. So -hmm. 8 minus 11. So I can write -3 as, no, I can't. I can write -3 as 5 minus, oh, let's do a different, it's not the same numbers, 9 minus 12. So I can write -3 as 5 minus 8 and is 9 minus 12. And so 5, 8 is the same as 9, 12 if, well, let's see, these are equal. Oh, shoot. 5 minus 8 is the same as 9 minus 12. If, well, let's add some things. If 5 plus 12 is same as 9 plus 8. Oh, okay. So I have that 5, 8 is the same as 9, 12. If 5 plus 12 is the same as 8 plus 9. So AB, so this is AB, is the same as CD, CD, if A plus D, this plus this, is the same as this guy plus that guy, B plus C. So it's just saying that if you represented -3 in two different ways, that they're the same. And so it's two different subtractions. So really, I think in my head, A comma B as denoting A minus B. So in my head, I'm thinking somehow I'm subtracting A and B. Okay, so let's define addition. So where, and I guess I should say here, where A, B, C, and D are all whole numbers. So now I'm defining this equivalence relation in terms of addition that we've already defined. We defined addition on whole numbers, and I can add whole numbers. So I was not able to do, in my mind I said A minus B, but the problem is I don't know what, A minus B is. That doesn't make any sense yet, but I do know what A plus B means if I'm dealing only with whole numbers. So that's why we defined it this way. So now let's define addition on this set of integers. And so let A, B, C, and D be whole numbers. Then I'll define addition of these two integers as follows. So suppose you have some equivalence class, some ordered pair AB quotient, some ordered pair AB quotient with this equivalence relation, added to, CD with this quotient out with this equivalence relation. Then this should equal A plus C, comma, B plus D quotient out this quotient relation. So what this says is, 5 minus 3 plus 4 minus 12 is the same as 5 plus 4 minus 3 plus 12. Voila. So it says A plus B. I'm sorry, that's a C. A plus C. And then the minuses are, that's a B and a D. B plus D. And notice that this, because you're pulling out the minus sign, now becomes a plus, and we know how to add. So now we've defined this addition as follows. Multiplication. So now let's define multiplication. So let A be a whole number, B be a whole number, C be a whole number, D be a whole number. Then A, B, quotient the equivalence relation, times CD, quotient this equivalence relation, is A times C. Notice that we're using the, I'll just say that in general. Notice that we're using the multiplication and addition that we have defined previously for whole numbers. And we're only dealing with whole numbers, so all of these are well defined. And then we're taking the quotient with the equivalence relation. Okay, so A comma B times C comma D is A times C plus B times D, comma, A times D plus B times C. So let's see. Actually, let me use A's and B. I should have been using A's and B's because that would have made maybe better sense. A minus B. Let's redo that, right? So this would have said A plus C minus B plus D. And that corresponds nicely to that. So now let's do it. A minus B times C minus D is AC And then if I do an AD, that's a minus AD. And then this will give me a minus BC. And this will give me a plus BD. So multiplying that out, I get this. So I get, voila, AB dot CD is A times C plus B times D, comma, plus B times C. So that's how I get these relationships. I just think of this as A minus B, C minus D. Okay. Note that the function f, taking the set of whole numbers to the whole numbers, cross the whole numbers, quotient it out with its equivalence relation, such that f at m is equal to m comma 0 over this equivalence relation is injective. And for m and n in the set of whole numbers, f of m plus n is equal to f of m plus f of n in the set of integers, and f of m times n is equal to f of m times f of n. So this gives us a, well, homomorphism between the two. Also, the addition for integers, multiplication for integers are well defined. And we denote 0, comma a, modded out by this equivalence relation, as just minus a. Then everything that I said from before works, and it just gives you the same sort of notation that we're used to looking at. Rational numbers. So rational numbers are numbers of the form P over Q, where P is an integer and Q is a non-zero integer. So let's define the set of integers as the Cartesian product of the integers with itself, where I take away 0. So I take away 0. So this is the point 0, comma 0 with this equivalence relation. And I quotient this with the equivalence relation for the set of rational numbers, where A, comma B is equivalent to C, comma D in the set of, well, this rational equivalence relation is that A times D, comma B times Z. That's not clear. If okay, there. That sounds much better. Okay, so we can think of this as follows. The A comma B is just A over B is equal to C over D if cross multiply AD equals BC. And these are all integers. And so since they're integers, I can just get rid of this is well defined. And so the multiplication, since these are integers, multiplication is defined as far as integers is concerned. Okay, so zero. So I have to get rid of the zero here. This is a little stricter than it should be, but it's good enough. Okay, so where, okay, I have here A is an integer, B is an integer that is not 0, C is an integer, and D is an integer that's not 0. We can denote this by 0 using the embedding of the whole numbers in the integers. Okay, so how do we define addition? So A comma B plus C comma D is AD plus BC comma BD. So how do I define the addition? A over B plus C over D, get a common denominator. So multiply by D, multiply by B. And so you get AD plus BC over BD. And so A over B plus C over D is equal to A times D plus B times C over B times D. It's how you always would add to fractions. Notice that A, B, C, and D are all integers. So multiplication, addition in integers is all defined. How do I multiply? Well, multiplication's easy. You multiply numerators and denominators. So A over B times C over D is B times D. Note F, going from the set of integers to the set of rational numbers, such that f of m is equal to m comma 1 quotienting out with this equivalence relation. So this is just some AB over the equivalence relation Z for some whole numbers A and B. This is equivalent to this one here is the equivalence class of 1 comma 0 over the equivalence class of integers, where 0 is a whole number and 1's a whole number. Okay. This is injective for m being an integer and n being an integer. F of m plus n, these are integers, so this is integer addition, is f of m plus f of n. These are now rational numbers, so this is rational addition. F of m times n, these are integers, so this is integer multiplication, is f of m times f of n. These are rational numbers, and this is a rational multiplication. And again, multiplication and addition are well defined for integers. To construct the real numbers, well, it's too hard. Most constructions use axiom of choice with an upper bound has at least upper bound. Okay, so if you have some upper bound, meaning that it is bigger than all members of the set A, then you have at least upper bound. So this is upper bound, this is also upper bound. Well, eventually, maybe you have one that's the smallest one, the least one. And the least upper bound principle says that for any set of real numbers, you always have a least upper bound. Let's do some examples. On page 760, prove each formula by induction if possible. Problem number 10. 1 plus 3 plus 5 plus ... 2n minus 1 is n squared. So let's try to prove this. So first, let's do the initial case. So let's try to prove the initial case. And so, well, 1 plus, you only do it up to 1, is equal to 1. Next, 1 squared is 1. So therefore, these are equal. Therefore, 1 plus 3 plus 5 plus 2n minus 1 is equal to n squared when n is equal to 1. So I just plugged in n equals 1 here, n equals 1 here. So this just only included this one term. So this is true when n equals 1. So your first domino falls. Next, let's do the induction case. Oh, and I guess I really should say since 2n minus 1 is equal to 1. Okay, so that's why this only had one term in it. So now let's do the induction case. So in the induction case, we're going to assume that some domino falls. Then I want to show that if I assume that one domino falls, that will imply the next domino falls. And so let's assume that 1 plus 3 plus 5 plus, and maybe I'll call it k, plus 2k minus 1. Assume that this is equal to k squared. Then let's look at 1, the next thing. 1 plus 3 plus 5 plus, keep adding, 2k minus 1 plus the next term, 2k plus 1 minus 1. Okay. So what I've done is I've added up this along with its next term. And let's see what happens. Well, I know that these first terms is equal to k squared. So I know that these are equal to k squared by the induction hypothesis. So this is called the induction hypothesis, this assumption that we're making. Let me multiply 2 inside the parentheses to simplify this. So 2k plus 2 minus 1. So this is equal to k squared plus 2k plus 1, combined like terms. Factoring, this is just k plus 1. But now I've shown what I wanted to show, that if I assume that some domino falls, the kth domino falls, then the k plus first domino, notice it also falls, because if I replace k here by k plus 1, this statement is now true. And so if the kth domino fell, then the k plus first domino also falls. And so therefore, by the principle of mathematical induction, and I guess just so that you know how that I'm proving this, we usually start off with PF to say that we're starting the proof. So now, therefore, by the principle of mathematical induction, we've shown the following. 1 plus 3 plus 5 plus 2n minus 1 is n squared for all n. And that's what you wanted to show. So now at the end, we write QED, meaning I'm done. So the PF at the beginning says I'm starting. The QED at the end says I'm done. Okay. Let me do problem 25.
Professor, do we have to write
Prove
that in our
x
exam?
minus y is a factor of x to the n minus y to the n. Hint, consider subtracting x, y to the k to the binomial x to the k minus y to the k, x to the k plus 1 minus y to the k plus 1. Okay.
I have a
So
question.
let's prove this. So let's first do the initial case.
Excuse me, I have a question.
And so x minus y is a factor of x to the first minus y to the first, because x minus y is the same as x to the first minus y to the first. Okay. So thus, x minus y is a factor of x to the n minus y to the n when n equals 1. So I've shown that the initial case holds. Let's do the induction case. Let's assume that x minus y is a factor of x to the k minus y to the k for some natural number n. Then, well, let's see. Well, this means that, and maybe I'll write this. So that means that there is some polynomial of degree k, let's say. Oh, of degree k minus 1, actually. There's some polynomial of degree k minus 1. In x and y, such that x to the k minus y to the k is some polynomial in x and y times x minus y. That's what it means to be a factor of, it doesn't really matter. if I write it either way. Okay. And so that means that this is some, that you have some factor times something times x minus y. Okay, so let's do this. So I have x to the k plus 1 minus y to the k plus 1. Let's write that strangely as x to the k plus 1 minus x y to the k plus x y to the k minus y to the k plus 1. And that is, I believe, exactly what they said. So they said here, consider subtracting and adding y to the k, x y to the k to this x to the k plus 1 minus y to the k plus 1. So that's all I've done here. I've just done what they told me, to subtract x to the k, x y to the k, and then add it back x y to the k. So I've subtracted something and I've added it back. So in total, I've done nothing to this. So this is the same as, well, let's group and the last two terms. Let's factor out x. Let's factor out y. To the k. Okay. And now let's use the fact that, well, then this is why I use this notation. So I needed a notation for this factor. So I said, well, x to the k minus y to the k, let's write it in this fashion. So x times p k minus 1 xk p to the k minus 1 of xy times x minus y plus yk x minus y. So now I can factor out x minus y because x minus y is in common in both. And what remains is x p to the k minus 1 xy plus y to the k. So this is a polynomial in x and y of degree k, which is good. So maybe I can write this as x minus y times p to the k xy, where p to the k xy is equal to x p to the k minus 1 xy plus y to the k. So all I've done is I've just rewritten what's in the brackets. Well, this is a polynomial. In x and y. And the degree of this polynomial is just k. This is the degree k minus 1. You multiply by some x, so that would be a degree of 1 higher, possibly. And this is, well, y to the k is a polynomial with degree k. So sum of two polynomials with degree k is just a polynomial with degree k, or less. So it's a polynomial of degree k or less. Maybe I should actually just say that, because it could be, it might actually, these might cancel out somehow. They won't actually, because that's an x, but it really doesn't matter. It will actually be a degree of, it will actually be equal to k. But this implies that x minus y is a factor of x to the k plus 1 minus y to the k plus 1. Since I found that I could, that this was equal to some x minus y times some polynomial. And so I've shown that the induction step works. And so therefore, by the principle of mathematical induction, I have that x minus y is a factor of x to the n minus y to the n for every natural number n. And that's what I wanted to show. Okay, good. So that finishes off